Our next speaker is Arthur Prat-Carrabin from Columbia University, and he did his PhD in cognitive neuroscience at École Normale Supérieure in Paris, and is now a postdoc in the Cognition and Decision Lab of the Economics Department at Columbia University. Arthur enjoys theoretical investigation as well as experimental work. A first axis of his work focuses on approximate Bayesian inference and decision-making under uncertainty. A second axis relates to questions of efficient coding of external information, which is what he's going to talk about today. He works with Professor Michael Woodford, and he has a recent bioRxiv paper out with the same title as the talk he's going to be giving today. Welcome, Arthur. You are muted. Dimitra, could you unmute him, please? Or
okay, I should be back on mic. Can you hear me?
Yes, we can hear you.
Okay. All right, so yeah, thank you, Manu. So indeed, I'm going to talk about efficient coding, and sorry, is this? Yeah. So more like specifically, I'm interested in why the human brain produces biases when estimating quantities or magnitudes. And in this project, we propose to an explanation that like biased judgments about quantities and magnitudes reflect optimal decoding of noisy mental representations of these magnitudes. And so we'll see that this will predict that the bias in the estimation of a magnitude or a quantity will depend on the variation of the imprecision in the representation as a function of the quantity. So we'll be interested in how the bias and the noise vary together. And in addition, we think that there is a good reason for which the imprecision of the representations might vary with the value of the quantity. And this reason is efficient coding, and which predict that the encoding should depend on the prior expression of the quantity, of the natural statistics of the quantity. So we look at this in the context of number perception, and we design an average comparison task in which we show to subjects, so human subjects, we show 10 numbers, 5 red numbers and 5 green numbers. And then we ask the subject to choose the color with the larger average. So they need to look at these numbers and then choose the color with the larger average. So we find that there seems to be noise in the decisions of subjects, so the probability of choosing one color is a sigmoidal function of the true difference between the empirical averages and not a step function. And in addition, the weight of a number in the decision appears to be a nonlinear function of the number, while for an optimal observer, it is a linear function. So we propose a model of encoding decoding. In the encoding step of this model, the presentation of a number x elicits in the brain a series of n random signals, or I. And then in the decoding step, an estimate x hat is inferred deterministically from R as the maximum likelihood estimator of x given R. So the MLE, so the maximum likelihood estimator, has a variance, which is the inverse of the Fisher information. But it also has a bias, which is also expressed as a function of the Fisher information. In fact, as the derivative of the inverse of the Fisher information. So this, thus we have a model in which the estimate x hat of a number x has some variance and some bias, and both of which depend on the value of the number. And in addition, you can see immediately that there is going to be a relation between the bias and the variance, which is this one, that the bias equal to 1/4 of the derivative of the variance. And so this relation, so we find evidence for this relation in our data, and it's a relation that's very close to the Wien-Stoker law of human perception that relates the discrimination threshold in perceptual task to the derivative of the bias. So this relation has been verified in many perceptual experiments. So you might wonder why would the variance vary with the value of the number? What would the precision of the encoding vary with the value of the number? And one possible answer is efficient coding. So efficient coding predicts that the precision with which you encode the number or like a stimulus should depend on the statistics of the stimulus. So one thing I didn't tell you about our task is that we run this task with 3 different conditions that differ by the prior distribution from which we sample the numbers. So this prior can be downward, and so small numbers are more likely, or it could be uniform, or it could be upwards, and large numbers are more likely in our task. So we fit our model, and so we fit the Fisher information function that appears in our model. We fit it to subject data, and we find that it seems adapted to the prior. So in the downward prior condition, the Fisher information is also downward, and in the upward prior condition, the Fisher information fitted to subject data appears to be mostly upward. So, and in addition, this is our best fitting model, and it captures the aspect of the patterns in behavior that I talked about earlier. So in summary, I introduced an encoding decoding model in which the encoding was characterized by the Fisher information function, and the decoding makes use of the maximum likelihood estimator. This model predicts a relation between the bias and the variance of the estimates. It was our best fitting model, and it yields a Fisher information function fitted to subject data that seems efficiently adapted to the prior. Thank you.
Thank you, Arthur. That was concise and great. That was very clear. Thank you so much.
And I have like suggestions for our questions.
That's always helpful. So let me ask a question not on this list first. So how would you account for any variation from the Fisher information that is predicted by an MLE? So what other alternatives could there be? For example, in your data with the flat prior, you had Fisher information that at least on one side looked significantly different. It would seem like. So how would you? What other models could there be in order to explain that?
So sorry, I don't know if you can hear it, but my computer is kind of stuck. But so I can't go back to the slide for some reason.
Okay. We can hear you though.
Oh, okay, so it's moving on its own. Okay, I don't know what's going on. I don't know exactly. So first of all, what I've shown here is so the Fisher information fitted to subject data. The truth is I don't know exactly what the optimal Fisher information would be in this task. In the literature, there are like results on efficient coding that will tell you that to maximize the mutual information between the stimulus and the internal representation, you should have a Fisher information that is proportional to the square of the prior. And so this is why here I've plotted the square root of the Fisher information versus the and the prior. But in real life, no one ever asks you to maximize the mutual information. In my experiment, you were rewarded by the amount that you chose, like the red or green. So this is what you should maximize. And so that's the first thing. And the truth, it turns out that in this task, it's very hard to determine what exactly should be the optimal feature information. And another aspect is that to derive a result of this kind of like the relation between the square root of feature information and the prior, you do have to assume a small noise, and things get much more complicated if your noise is not vanishing. And so the optimal, I don't know. But in any case, what's really weird here is that it's in the middle case with the uniform prior, it should be symmetric. And any solution would be optimal solution would be symmetric. So we don't find that it's symmetric. So I'm not sure why. One possible interpretation is that people are used to, so the natural distribution of numbers in real life is kind of skewed, like it's log normal.
Benford's law.
Or like it's or something like this. So yeah, so that might be an explanation for this asymmetry. Yeah.
Thank you. So we have a question from the audience. Ari Benjamin, if you'd like to come on and ask your question, that'd be great.
Hi, how are you? Yeah, I was. It's actually very related to what was just asked, and I'm wondering if you ran a condition in which you did not tell the subjects what the distribution was to try to suss out what the natural prior, or to see if you could identify something of the form of Benford's law.
So I could do that. The only problem is that they might learn. I mean, so if I show them something, I have to choose the distribution from which I sample. And so eventually, I guess they will learn. So maybe if I just look at the beginning and fit only that, yeah, actually maybe, or yeah, instead of asking many questions to one subject, I can ask many subjects one question, and then the number that I show will be for that person from his natural prior. Yeah, that's a possibility. Here, let's say that I like when designing a task to make the things like very clear for the subject, and so actually we showed them, we told them explicitly what the distribution was. We showed them the PDF, but also we showed them lots of samples from the actual distribution that we were about to use, so that we hope that they learn about the statistics. What people have in their mind spontaneously like this as a prior for the distribution, I'm not sure. So you see in the literature, they say it's something, yeah, so Benford, but I think Benford is for figures, right? Or for like the first figures in numbers.
First numbers in a set of naturally occurring numbers, typically.
Yeah, so I don't know what's, yeah, I don't know. And I don't know what's the natural distribution, and I don't know if you could actually prove that, measure that in subjects with an experiment, but maybe.
So related to that, how much experience did the subjects have with the trial before this data was collected?
So here, so each subject did like a 1 hour session, divided in 2 blocks. So they did 2 conditions out of the 3. Each subject did 2. And they had, so I showed them 200 times, I think 200 samples from the distribution. So they don't have to do anything, they just look at numbers. So hopefully they get used to it and they adapt their encoding. And then, if I'm not mistaken, I think they have 200 trials. And so in one trial, you see 10 numbers. So that's a lot of numbers, and it goes pretty fast because it's like half a second per number. So it goes pretty fast. but they are not, I mean, they are not trained to do the task, I would say, before I measure.
I see. So I guess my question was, do they do multiple trials, multiple sets of trials with the same prior?
Oh yeah, they do 200 trials with one
200 trials.
For one prior.
Yeah, absolutely. Okay, so that was my question. Yeah, so that's great. But it's pretty amazing that you can actually reconstruct these priors relatively well from the subject's data. That's pretty impressive. Also, thank you so much, Harry, for asking the question. Are there any more questions for Arthur? Going once, twice. I don't see any. And so thank you so much, Arthur, for your talk.
Thank you.
Wonderful. And also thank you so much to the audience. And I especially at this point want to thank Dimitra Maoutsa, who's in the back end for this room, who's been fielding all of the questions and typing all of the chats to the panelists and attendees. Thank you so much, everyone. Have a wonderful morning, evening, night.